Welcome to our MAQ Academy, and we have organized the webinar sessions to talk mostly about how to handle or reduce the vibrations in the machining industry today. The seminar is organized in 3 sessions. The first one, we focus mostly on the introduction part to get a picture of what we are talking about in the seminar. The second session, we talk mostly about the current solutions for reducing vibrations in machining. And the session 3, we're going to talk about what is MAQ and what do we do differently to reduce the vibrations in today's machining industry. On the right-hand side, you have my name and my email and also contact information, phone number, and so on. And please don't hesitate to raise a hand or to send me some emails if you have any particular questions about the vibration problems in the machining industry today. I thank you all for coming to join this session. So let's spend some time together to share the knowledge and experience that we all have in our daily job, let's say. First off, I would like to spend a few minutes to get a short introduction about myself. I always had a passion for mechanical engineering, and that's why I spent almost 15 or 20 years to dig into this area. I got my master's in KTH, the Royal Institute of Technology in Sweden, and right afterwards I followed a PhD program for 5 years to do the research about reducing vibrations in machining industry. And after that, I took a postdoc position in the same department, same research group, and mostly focusing on a wider scope of the vibration issues in the modern industry for machining. And after that, I together with my colleagues, I created the MAQ and in the company. To the right-hand side, you can see a picture of me that was taken 2 years back, and I have registered more than 7 patents in the area of reducing vibrations in the machining, and published more than 7 journal articles in the academy. And currently, I'm still serving actively as reviewers for some of the international journals. So to keep an eye and get a feeling for what's going on in the research side. Machining systems, there are major 3 categories. The first one is the external disturbance that is caused by a pump or a servo drive that is located somewhere else in the shop floor, and to handle that, you have to either shut down the pump or the servo drive, or you make an isolation of the machine to the external disturbance. And the other 2 types are categorized as the forced vibrations. And one typical example is the tooth passing frequency in mini application, where the cutting edge gets engaged and disengaged with the workpiece, and that excites a vibration to the machine tool system. And the third category we talk mostly is about the chatter, so to say, the self-excited vibration, and that is actually a phenomenon that occurs naturally in machining, and is quite complex to resolve because of its self-exciting character. And this is also a typical problem that limits the productivity, such as the feed speed and tool engagement and so on. Today, the presentation, we're going to focus mostly on the latter 2 parts. One is the forced vibration and one is the chatter, because those 2 are mostly so to say difficult to handle compared to the external disturbance. Why is this interesting? The vibration itself is rather a complex phenomenon, both in education and also in daily life in mechanical engineering. It is a complex phenomenon that limits the productivity in machining. It costs a few tens of millions of dollars per day on the globe. And it also creates the pressure on the conflict material, the tungsten material. And people are dying for mining this material on the globe every day. And this is also creating a unnecessary wasting of energy due to low productivity. So it is really worth us to spend some time to understand what we have as vibrations in machining. I took as a challenge for today's manufacturing, we have one example here where we turn the raw workpiece material into steel bushings, and in some of the steps we have the turning operations. And let's say that we have made the same investment to build 2 production lines. We bought the same machines, used the same tools, and the difference is that all of a sudden, after a long series production, we realized that even though we have bought the same machine, same model, same fixtures, same tools, use the same process parameter, the 2 machines that they looks identical, they have very different performance in terms of the number of parts that can be machined by a tool change, and in terms of the quality issue, for example, the rejection rates, the recorded claimed number of interruptions, and so on. So when you buy a machine, they clearly categorize the power rating for this machine, the maximum force, the traverse of the axis, and so on. But they will never tell you how many parts you can machine per tool change. And this is actually because it's impossible or not impossible, but it's very difficult to predict the performance of the machining process in a particular machine. So this I define as the challenge of today's manufacturing, which is unpredictable tool life and unpredictable reliability. And so far, there has been no solution in both academy and in actual production. This is actually associated with the dynamic property of machine structures, and this is why we have to spend so much effort into understanding the vibrations in machining process. As an overview of the machining process with vibrations, when a cutting tool starts to engage with the workpiece, we start to shear off the metal and we produce chips. When we shear off the metal, we create new surfaces, and the process of creating new surface is associated or is equipped with the process of exciting the acoustic wave or the vibration waves that transfers inside the tool body structure. So the waves that get propagated, they transmit inside of both the machine tool and also the workpiece, and these waves starts to get reflected on several boundaries, and some of the waves starts to cancel each other, and some of the waves starts to build up with each other and excite more vibrations. And once the tool engages with the workpiece, we will also hear the acoustic radiation. The sound tells that the tool is not cutting the material. This is a very high-level overview of the machining, and it tells us that the vibration acoustic excitation is naturally occurring in the machining process, and it is because we are shearing off the metal. The difference it makes, first of all, when you have a vibration and compared to the case where you don't have it, the very apparent difference is the surface finish and the tool wear. Apart from that, we also have seen the difference in the geometric accuracy and also the geometric tolerance of the machine part. The process reliability plus the productivity also gets affected by the vibrations. So this is the difference we are talking about. And as we all know, for machinists, it's important to have a reliable process, and it's important to have a high productivity so that we save the cost. Let's spend a few minutes to understand what is a vibration. On the animation on the left-hand side, I have a single degree of freedom system where I have a mass suspended by a spring. And imagine that I'm trying to excite a structure with 1 Newton force, and I try to excite the structure with different frequencies. What we can see is that all of a sudden we will start to realize that at some of the frequencies, the structure gets very easy to be excited with a small force. And on the other frequencies, the structure gets not so easy to be excited. And we start to realize, oh, the structure actually, the system by itself, has a natural frequency where it gets easily to be excited. There are, of course, equations developed by mechanists, and if you have time and you want to know more, you can always dig into look into the details. But today, what I want to tell is that every mechanical system has a natural frequency or a more natural frequencies where it gets easily to be excited with a very small force. So very small force can create a big displacement or big vibration in a system. And if you look at a cutting tool in this case, a cutting tool, if we have mounted a cutting tool into a machine tool structure and we apply force and we look at the behavior of the tool, so we measure the displacement of the point close to the cutting edge, and we actually also see that this cutting tool also gets easy to be excited over certain frequencies, and we can model the cutting tool body as a single degree of freedom because we realize that, oh, there are frequencies where it gets easily excited. So this is the frequency information we're talking about in a machine tool structure. A machine tool has natural frequencies. And then remember that we have been trying to define the equations to calculate the natural frequency of a cutting tool by the mass and its stiffness. And if we look into the machine bed, for example, I mean a complete machine, then we start to think, I mean, we have said the stiffness and mass decides the frequency where the system gets mostly easy to be excited. And if we look at the mini machine in this case, we start to realize that there are plenty of stiffness parameters like the machine feet, the ball screw drive, oil bearings, taper clamps, column structure, so on and so on. All of these interfaces, they have a stiffness decided. And if you look at the mass distribution, such as the clamped tool, the workpiece, the spindle hang, column hang, and the work holding fixtures and so on, all of them has a different mass distributed in a structure in a 3D space. The question came up right away is that how many frequencies are there in this machine? How many natural frequencies are there? And if you look at a cutting tool, and this is a very typical cantilever beam structure where it's bent, mostly in the bending motion. And if we apply a force on the cantilever beam structure, we all know that when we change the frequency of the exciting force and we look at the displacement, the same cantilever beam can be excited by many frequencies. So it has a few more frequencies than what we thought about, that the structure can get easily to be excited. And we can imagine this cantilever beam as composing thousands or millions of small springs and small masses that are connected with each other. And that's why we can see several modes or plenty of modes that in the same cantilever beam structure. And it is actually true that a cantilever beam structure has unlimited number of modes, and it only depends on the frequency that you can do analysis with. So a vibration mode consists of a frequency and some other mode parameters such as the stiffness, mass, and damping, and so on. But it is quite important to remember that a vibration mode consists of a frequency. And each geometry has an unlimited number of modes or natural frequency that are decided by the stiffness and mass. And it is important where we define as the stiffness and what we define as the mass that is in the system, and it's unlimited number. The structure stiffness actually also depends on the wear and tear of the components, the temperature, humidity, and so on. And also the mass distribution is constantly changing, particularly in machining because of the movement of the spindle on columns, and also because of we are removing material on the workpiece, so the mass is constantly changing. So this really brings the problem to the vibration issue in machining because we have a stiffness that is changing, and we also have a mass that is changing. So it is hard for us to decide or determine where's the frequency we're looking at. There are methods that has been developed so far to measure the frequency, the mode frequencies of a typical machine. Side of the picture, and we mount a few accelerometer on the tool body to measure the vibrations. What we do is that we supply a impulse force by the hammer, and we measure the acceleration. And what we do is that we use the transformation calculations to look at the input and output on the frequency domain. And this is the this is the principle, or this is the basic how we look at the time domain signal and how do we transform them into the frequency domain to look at them on the frequency domain. And we use the output to be divided by the input, and then we realize that, oh, now we can find out which frequencies are there that the tool gets easily to be excited. This is how we get the mode frequencies of a typical machine tool structure. And then it's time for us to introduce about chatter. The chatter issue, I mean, we have been talking about the frequency most of the time, but the tool chatter is a statement made by Taylor in 1907, is that it is one of the most obscure problem that is facing the machinist. So the same problem has been bothering us for centuries, and it was until 1960s we were able to explain what is the tool chatter and starts to build the foundation for the academy. And after that, we actually realized the earliest documentation was actually observed by Galileo Galilei in 1638 when he was scribing a copper chisel on a metal surface. And that was actually the earliest documentation about tool chatter. If you're interested, you can search on Google and you can find it in Wikipedia if you want. The chatter brings the bad surface finish, and it existed in both internal and external machining. And it is one of the most difficult problems to resolve. The definition for tool chatter, it is a vibration phenomenon that occurs naturally in machining processes. And it is caused by the interaction between the machining process and the machine tool structure. To the right-hand side, you have a small animation. When the cutting edge starts to get engaged with the workpiece that is rotating, the cutting force excites the cutting tool structure, and a vibration starts to build up in the system. And as the time goes on, the leftover surface marks on the workpiece starts to have an impact on the next excitation to the same cutting tool structure, so that the vibration starts to get amplified. It starts to grow over the time. And this is the basic principle for what we define as the tool chatter. It is affected by a previous cutting profile on the surface and the current cutting profile. And these two cutting profile decides the chip thickness or chip load that is applied on the cutting tool. And this chip load has the frequency information of the cutting tool structure, and that is what we call as a tool chatter. And the foundation, as I have just mentioned, it was created built in 1960 by Tobias and a few of his colleagues. He's very famous in this area. We were able to build up a closed loop system. And for example, in this case, when we have a cutting force applied on the elastic structure of the machine, the tool holder and so on, and it affects the displacement of the elastic structure. And this displacement and that will again affect the cutting process to decide what is the cutting force. So the cutting force and the displacement starts to decide what is the next cutting force coming into the elastic structure. And this speeds up a closed loop system or feedback loop. And as we all know, for a signal processing part, when you have a closed loop system, then you have the boundaries where the system gets stable or unstable, depends on the interaction between the two coupled systems. We take a look at a simple turning process, for example. Let's imagine we have a workpiece that is rotating at 5,000 RPM, and it takes 12 milliseconds for this workpiece to rotate one round. And we have a machine tool that vibrates, has a natural frequency at 1000 Hertz. It takes 1 millisecond for this tool to vibrate for one cycle. So when the workpiece has been rotating for one cycle, the tool will leave 12 waves on the surface. And if we look at the cross section in the cut, we can see that, when you have 12 waves, the previous chip formation surface and the current chip formation surface, they are in line with each other. They are in phase with each other. And we have a constant chip thickness that is being removed by the two. And that means we have mostly we have the static part of the cutting force. We don't have the dynamic force anymore because it's constant, theoretically. And when we try to decrease the rotation speed of the workpiece, we start to realize that, oh, now all of a sudden they start to be slowly and slowly out of phase. And when you have the 4,800 RPM, the previous cut surface and the current cut surface, they create the cutting force that is changing from zero to the maximum and back to zero again. And it is important to remember this profile or this cutting force now has the information of this 1000 hertz. So we are trying to excite the two structure with its natural frequency. And how does that sound? Because the two structure gets very easily be excited. That means 4,800 RPM will excite more vibration compared to 5,000 RPM. And if we reduce the rotation speed of the workpiece a bit further, then we all of a sudden start to realize that, oh, now we are back to a condition where the chip thickness gets almost constant again. So this is the very basic explanation for what is two chatter, and this is why when you do the mini application, for example, you are suggested to change to test the different rotation speed of the mini cutter to find out which RPM is the most preferred. And if you change the rotation speed of the workpiece or the two, you start to go across the unstable and stable regions. So this is the foundation for the two chatter. And it does not always work because there are many things that are associated or affecting the performance of the machine tool system in the overall picture. And let's look at the forced vibration in this case. And we are using a very big face meet to meet the pocket features on the engine block. And the forced vibrations, the excitation frequency can be decided by the spindle speed, the number of inserts, and we can calculate what is the excitation frequency. And because we have the whole features on the surface, the excitation all of a sudden now is also decided by the time elapsed between two engagements. And if we mount a accelerometer on the cutting tool structure and we look at the acceleration signal we get, and then we map them, we collect them and we map them out we stack them up, the signals we have measured on the frequency domain, and we start to realize that, oh, now it's really hard for us to decide how many modes are there because it's many frequencies we're looking at. So this is the challenge because remember, I mean the machine tool structure by itself, I mean the stiffness, the Mason zone is constantly changing. So it is very hard for us to determine which is the main mode. And a typical machine structure always get excited over a very wide frequency band. So a summary for the first session. A vibration is a natural phenomenon that occurs in machining. It is caused by the metal shearing process that emits the vibration waves that gets transmitted into the machine tool structure. Vibration typically occurs when the L/D ratio is above 4, and that is actually because it becomes to be more prominent and it becomes to be noticed. It doesn't mean that when you have a short L/D ratio, you don't have vibrations. You have vibrations anyhow. And the vibration limits the productivity together with the other challenges such as the carbon grade, the coatings, and the process planning part and so on. In the structure's vibration frequency affects both the forced vibrations and the tooth chatter. So it is important for us to understand where is the structure's vibration frequency located and what is the natural frequency of the structure. Today in machining, I mean, if we're talking about series production where high productivity is really demanded, try and error is still very often in modern machining when we have a hard time to understand where the problem comes from.